Today we are going to talk about basic electronic components found in every modern electronic device and their functions. We will look at their characteristics and explore their work principles. Then we're going to conduct a series of experiments illustrating their operation and application. This is Mattino. The most common and simple component is the resistor. Its one and only function in an electrical circuit is to reduce current. Here we can observe two identical light bulbs powered by two identical batteries. One bulb is wired directly to the battery, while the other in series with a resistor. As we can see, the second bulb is dimmer. The reason is because the resistor steals some of the battery's energy. As a result, the voltage on lamp number 2 is lower, while the voltage on lamp number 1 equals 4 volts, which is battery's voltage. In electronics, this phenomenon is called voltage drop, so we can say that 0.5 volts are dropped on the resistor. By design, a resistor is just a piece of metal, a conductor. As opposed to regular wires, however, a resistor resists the flow of current, partly turning it into heat. So the most important property of this component is its resistance. The less metal a resistor contains, the higher the resistance. The higher the resistance, the lower the current in the circuit, and the higher the voltage drop across resistor's terminals. Resistance is measured in ohms. This unit is named after the German physicist Georg Simon Ohm, who in fact discovered the relationship between current strength, voltage and resistance, today known as Ohm's law. The resistance is indicated on the body of the resistor by color code, which allows anyone to read the value no matter the orientation of the part on the board. The second very important property of a resistor is power rating. As you can see from our experiment, when connected in series with a resistor, a light bulb's intensity is reduced. But we all know that energy is neither created nor destroyed, which means that part of battery's energy is dissipated on the resistor as heat. At high current values, heating can be quite significant, so the resistor power rating is always chosen according to the load. As a rule, the higher the power rating, the larger the dimensions of the resistor. If you ignore the power rating requirements when building your circuit, your resistor may simply burn out and fail. There are fixed and variable resistors. A variable resistor is a device whose electric resistance value can be adjusted. Variable resistors are basically used in two situations: when one needs to adjust a value while fine-tuning a circuit, or if it's necessary to change a parameter when utilizing the device. A volume knob on your car radio or a guitar amplifier would be a typical example of a variable resistor. One very important aspect must be understood. The amount of voltage drop across a resistor depends not only on its value, but also on a whole number of factors: current strength in the circuit, load behavior, power supply voltage, etc. So the drop on a fixed resistor is not constant and may actually vary. This means we cannot use this component to build a voltage stabilizer. But we will talk about step-down converters a bit later. Capacitor. This is perhaps the second most common electronic component after the resistor. The capacitor is used to store energy and can be charged using any DC source. After charging, the voltage on the capacitor will be equal to the voltage of the source. If you connect a charged capacitor to a load, it will release the accumulated energy. The amount of energy, or rather charge per unit of voltage, that a particular capacitor can store is called capacitance. The higher the capacitance of a capacitor, the longer it can power the load. Capacitance is measured in farads, a unit named after the English physicist Michael Faraday. 1 farad is very large capacitance, so in electronics, microfarads, nanofarads, and picofarads are commonly used. For some reason, a unit called millifarad is typically not used when indicating capacitance. You can, however, find it in measuring instruments, a multimeter for example. So when measuring capacitance, do not confuse it with microfarads. By design, a capacitor consists of 2 conductive plates. Between them is an insulating layer, also known as dielectric. The dielectric has a certain maximum voltage that it can withstand. When exceeded, an electrical breakdown occurs. So the second most important property of the capacitor is the voltage rating. Along with capacitance, it is always indicated on its body, and in no case should it be exceeded. In a way, a capacitor is similar to a rechargeable battery. But the essential difference is that a capacitor stores the electrical charge directly, while a battery first converts electrical energy into chemical energy, stores it, and then, when discharged, performs the reverse conversion. On the other hand, capacitance of a typical capacitor is significantly lower than the capacity of a battery, so capacitors, as a rule, are not used as power supplies. At the same time, they are simply indispensable as filtering devices, and in most circuits they can be found connected in parallel with the power supply. Such capacitors ensure stability, minimize voltage transients, and may temporarily take over the power of the circuit in case of short-term voltage drops. In this situation, a parameter called ESR is of vital importance. ESR stands for equivalent series resistance and is a value representing the loss of useful energy in a circuit. ESR is a value that shows how fast a capacitor can deliver energy to a load and is measured in ohms. The lower the ESR, the higher the performance of the capacitor. You cannot measure ESR with a multimeter. You need to utilize a specialized device for this purpose. For example, the GM328 universal tester, which I have made a separate video about. You can find a link to it in the description. Diode. Diode is the most basic type of semiconductor. A diode, just like a resistor or a capacitor, has only 2 terminals. Its chief feature, as you might guess from the name, is the ability to conduct electric current only in one direction and turn into a dielectric if current direction is reversed. The symbol for a diode in a circuit diagram is a triangle pointing toward a straight line perpendicular to the wire. The orientation of the triangle indicates the direction in which current is permitted. The electrode marked with a triangle is called anode, and the one with the line, cathode. The current flows in from an outside circuit through anode and flows out through cathode. The cathode and anode are sometimes called negative and positive poles respectively, since it is the polarity in which voltage must be applied to the diode so that it conducts electric current, or, as they say in electronics, becomes forward biased. Of course, this rule is also true for LEDs. And it's actually quite easy to remember, because the shape of the cathode coincides with the minus sign. A similar technique is used for marking diodes. The cathode is indicated by a white stripe on their body. In a circuit, diode is most often used to rectify alternating current, AC, and it's almost indispensable as a rectifier. For that purpose, 4 diodes are usually connected in a bridge, like this. Alternating current is fed here, and direct current is taken from here. The diode bridge circuit was invented by Polish electrotechnician Karol Polak and patented in 1895. These days, diode bridge is mostly manufactured as a dedicated module with 4 terminals, and as the bridge rectifier produces a pulsating DC voltage, in real circuits you will always see a capacitor wired in parallel to the output of the bridge. The purpose of the capacitor is to provide a smoother output voltage and prevent voltage spikes. Diode, strictly speaking, is not a perfect conductor when forward biased, because, similar to the resistor, it exhibits voltage drop. However, contrary to the resistor, whose drop, as was noted above, depends on a number of factors, the drop across the diode is basically fixed and is usually around 0.6 to 0.7 volts. This particular feature can be used to build a simple step-down circuit. Let's say you have an old mobile phone that needs to be powered from a USB power supply without using a battery. The nominal voltage of a lithium-ion battery is approximately 3.7 volts, while the USB supply outputs 5 volts. If we take two diodes and connect them in series, the anode, of course, must be connected to the positive rail, that is, the red USB wire, we will get a voltage drop of about 1.4 volts, which is basically what we need. And what's really important here is that, provided that the USB supply produces exactly 5 volts, the voltage at the output of our circuit will also remain stable, no matter what happens to the load, the phone. So, by wiring several diodes in series, it's possible, if necessary, to come up with a larger fixed voltage drop. This method of stepping down the voltage works pretty well, but you can hardly call it convenient. For example, if you have to drop 12 volts, you will need as many as 20 diodes. Wouldn't it be nice to have a component with a fixed voltage drop that exceeds 0.7 volts? And such component exists. It's called Zener diode. A Zener diode looks very similar to a regular diode. Sometimes they can even be confused. When forward biased, the Zener diode works pretty much the same way as a regular diode, demonstrating voltage drop of about 0.7 volts. But if you apply voltage in reverse polarity, that is, reverse bias the Zener diode, it will also conduct electric current. And its voltage drop in reverse mode can range from 1 to several tens of volts, depending on the reverse breakdown voltage rating of the actual part. So the working polarity of a Zener diode is reversed, and its anode is usually connected to the negative power rail. In most cases, you can find out the voltage rating of a particular Zener diode only by the designation on the package, or by measuring it with a metering device, for example, the already mentioned GM328 universal tester. Most Zener diodes cannot be measured with a multimeter because the voltage across the probes is not high enough to reverse bias the component. You can also measure the Zener voltage drop with a regular voltmeter. All you have to do is apply voltage to diode's terminals that would be enough to reverse bias it, then measure the drop. However, you can do it, important, only if you've made sure the current strength in your circuit is limited. If you're using a lab power supply that allows to set maximum current, for example the DPS 5020, you need to set it to the minimum value. Or you can connect a resistor in series with your power supply. The value should be several kiloohms. Remember, at the very beginning of this video, we mentioned that resistors can limit current. As a result, by the way, we can come up with a simplistic voltage stabilizer circuit. As we can see, the lab power supply is set to 23 volts, but the Zener diode limits voltage at 16.4 volts. However, output current strength of such stabilizer will be very low, since current is limited by a resistor, and you cannot use it to power a mobile phone or a motor, for example. Now let us talk about inductive components. That's basically transformers and inductors. These devices are pretty simple by design. They consist of one or more coils of wire, called windings, usually centered on a ferrite core. Some transformers are oval, and some are rectangular. Some contain only a few turns, while the others, depending on their purpose, may have several thousands. There's another, also very common layout, in which core is made up of a solid ferrite ring. It's called a magnetic circuit, and the windings are laid around its circumference perpendicular to the tangent. Such devices are called toroidal transformers. The advantages of such design are smaller weight and dimensions, a reduced noise level, and most importantly, a higher efficiency. The obvious disadvantage of a toroid transformer is the more complex process of winding, which requires a special device. At the factory, however, toroid winding is performed by a robot, which significantly reduces production costs. The purpose of an electric transformer, or simply a transformer, is to transfer energy from one electric circuit to another without electrically connecting them to each other. Transformers can also be used to step up and step down voltage, and can be found in any power supply that plugs into a household wall outlet. A transformer has at least two windings. They are called primary and secondary. They are electrically isolated from each other. The input voltage is fed to the primary winding, and the output voltage is picked up from the secondary winding. When AC voltage is applied to the primary, the energy contained in electric current is converted into magnetism, which, passing through the magnetic core, then gets converted back into electricity at the secondary coil. And that's basically the method that allows transfer of electric energy without electrical contact. In general, it is possible to step down voltage in different ways, and strictly speaking, a transformer is not necessary to achieve this. But the main reason why transformers are used almost everywhere is user safety considerations. Any electronic device that assumes interaction with a human is not allowed to have a direct electrical connection to the wall outlet. As the transformer's windings are isolated by design, it can provide the so-called galvanic isolation, that is, isolation of output circuits from the input circuits. So anyone who uses, say, a USB charger does not have the slightest chance of being electrocuted by simultaneously touching the USB cable and, for example, a radiator heater, since there is no circuit between the mains plug and the output connector of the USB charger, which, as you can see, can be easily verified with a multimeter. If the multimeter detects a circuit in your case, your charger must go directly to the garbage bin. It's dangerous to use it. A transformer can only operate on alternating current. If you connect a light bulb to the secondary coil and a battery to the primary coil, the bulb will only flash once, but will not glow constantly. This is because transformers only transfer energy while the magnetic field inside the magnetic circuit is being changed, and the direct current cannot provide such change. The inductor, also called a choke or a reactor, is similar to the transformer by design and can also have a conventional or toroid layout. But unlike a transformer, the inductor has only one winding and only two terminals. The inductor, just like a capacitor, can store energy. However, it releases all energy immediately after the supply voltage is removed, unlike the capacitor, which can store it for a relatively long time. You can observe the operation of a choke with the help of two simple experiments. Here you can see a light bulb, a choke, and a battery. Let us connect all these elements in series. As we can see, when the bulb is wired through a choke, it does not light up instantly, but with some delay. This is because the moment the circuit is closed, part of the energy is stored in the magnetic circuit of the choke, that is, it's being charged. When the core of the choke is saturated, energy begins to flow into the load. Now let us wire the bulb and the choke in parallel. The bulb also turns on with a slight delay, but that is because the very first moment the choke imposes load on the battery. A more interesting effect is observed when the battery is disconnected. we can see that the bulb does not go out instantly, but gives an additional flash. This happens because once the supply voltage is removed, the inductor transfers the energy stored in its core to the bulb. Now let us modify the circuit a bit. It is known that the voltage spike that occurs on inductor's terminals, again unlike in a capacitor, has a reverse polarity. So, if we connect a diode in series with the bulb, we will have a chance to observe the process of choke discharging separately. Now the bulb flashes only when the power is turned off. The main physical property of a choke is its inductance. Inductance indicates the amount of energy a particular inductor can store and is measured in henries. The unit is named after the American scientist Joseph Henry, who discovered the phenomenon of self-induction. The inductor is one of the most important components in modern electronics, and its relevance is only increasing. Every power supply unit on the planet uses one nowadays. Another typical function of an inductor is high-frequency noise filtering. As we have observed, the inductor absorbs the primary voltage spike that occurs when power is applied to the bulb. In a similar way, being part of a power supply, it smooths out all sorts of spikes and noises that occur during the operation of the device. Inductors nowadays are also very commonly used in step-up and step-down DC-DC converters. And I would like to say a few words about the ferrite cores, also called ferrite beads, which can be seen on laptop power supplies, USB, and some other computer cables. Contrary to popular belief, they do not serve the purpose of protecting the device from external interference. It's actually the opposite: to limit and clean common mode noise generated from either a signal line or the power cable itself. The cable, due to its length, plays the role of an antenna, which can emit radio waves when your laptop or USB device operates. So, the ferrite toroid is needed to limit its electromagnetic interference. We have finally made it to the part where we speak about the component that I'd like to call the king of electronics. His Majesty, the transistor, ladies and gentlemen. In a nutshell, the purpose of the transistor is to amplify weak signals. That is why it's primarily used in audio and radio devices, amplifiers, tape recorders, radio receivers, television sets, microphones, etc. Today, its application is certainly not limited to this area, and the difficulty of understanding its operation is explained by the fact that, unlike a resistor or even a diode, the transistor is a very versatile element. It has several different modes of operation, which are determined, perhaps this is the most important thing to remember right away, primarily by how it is connected in a particular circuit. And of course, there are also several types of transistors, which have different properties and characteristics, depending on purpose and scope. Like I said, transistors are mostly used for amplifying signals. This is an Arduino LED flasher. As Atmega's outputs can sink 40 mA max, you pretty much cannot wire to it anything except a regular LED. But you can use a transistor switch to amplify its signal. As you can see, now we are flashing a light bulb. And if you install a more powerful transistor here, you can drive an even more powerful load accordingly. The transistor has 3 terminals. They are called emitter, collector, and base. So, when connecting, it is necessary to follow the diagram that shows their arrangement. In electronics, it's called pinout. You can always use the GM328 universal transistor tester to find it. For example, this part has the following pinout: base, collector, emitter. If you use transistor as a switch, collector is where you attach the load, and base is where you feed the control signal. And there are basically two types of transistors: N-type and P-type. In an NPN transistor, current flows from the collector to the emitter. In a PNP transistor, it's the opposite, from the emitter to the collector. Current flow direction, just like in a diode, is also reflected in transistor schematic symbol, the arrow. The transistor has many other important characteristics and properties. The most important one is the current gain. In our case, it's 68. The second important characteristic is the transistor's voltage rating. If exceeded, a breakdown may occur and the transistor will fail. The third important characteristic is the switching frequency. Transistors are either low frequency or high frequency. For example, if you install a low-frequency transistor in a switching power supply operating at a high frequency, the oscillations will not set in and the circuit will not work. If you're repairing a device and you are not able to replace a faulty transistor with the same type, these three characteristics, and of course also transistor's power rating, are basically the ones you need to consider when looking for a replacement. In the world of electronics, there exists another three-pole semiconductor called THYRISTOR, or SCR, silicon control rectifier. Basically, it's a diode having an extra terminal called gate, and its functionality is somewhat similar to the transistor, but the principles of operation are simpler and the scope is narrower. An SCR, like a transistor, can be used to drive a powerful load with a relatively weak signal. However, as opposed to the transistor, THYRISTOR retains its state while the power is on, even after the control signal had been removed. The SCR, similar to a diode, has an anode and a cathode, plus an additional switching input called the gate. The SCR, just like the diode, is connected in series with the load. However, our light bulb, as we can see, does not light up, although we have applied power in the correct polarity. The reason is that the THYRISTOR is off. To turn it on, we need to feed a pulse to the gate, like this. The bulb illuminates and stays on, despite the fact that we have removed the control signal from the gate. To turn the lamp off, we must either terminate the power to the entire circuit, or, alternatively, short-circuit the node with the cathode, which is the same from the point of view of the THYRISTOR. Now the SCR has returned to its original state, and we can repeat our experiment. It is thus possible to assemble a simple two-button switch using a THYRISTOR. One button will supply current to the gate to turn it on, and the second one will short the SCR poles to turn it off. Oddly enough, this is basically about all the THYRISTOR is capable of, that is, to work as a latch switch. In reality, latching is more of a disadvantage, because to turn the SCR off, you always need to utilize an additional circuit. Because of that feature, THYRISTORs are mostly used in AC circuits, where the oscillating sine wave, twice in a period, cuts off power to the THYRISTOR and resets it to the original state. And that would be it for today. As always, I'd love to see your comments. And if you'd like to purchase the equipment and components shown in this video, you will find the links in the description. Please don't forget to share this video in social media. This was Mattino. Be good.